Okay, here I am. Very good. So, wave forces, as I said. So wave forces, I am moving forward. If you have any question, problem, please let me know. Just 1 second, I'm opening the chat. Okay, very good. I'm writing on the chat. I am restarting for any question. Please write here. Now, wave forces. Wave forces are through the ship. We are talking about wave forces through the ship to the berth. And the waves cause a movement of the ship and therefore a forcing over the berth. A ship is a rigid body. We can consider the ship, as a rigid body here with 6 degrees of freedom. And you can look at the figure here. The 6 degrees of freedom of the ship. I go back now to the web page. So 6 degrees of freedom, and there is a link for the definition of degree of freedom, which for sure you already know. And these 6 degrees of freedom correspond to translation along the 3 directions of space and the rotation around them. It's also interesting to look at the terminology which is used in nautical terms. Ones that are impacted by waves, ship can undergo, as we know, as for wind, can undergo a rotational and or translational motion. So we have the 3 axes which identify the 6 degrees of freedom, and these axes are the longitudinal axis, the transversal axis, and the vertical axis. Now, the rotational movement around these 3 axes are roll, pitch, and yaw, respectively. Roll is the rotational movement the rotational movement around the longitudinal axis. Pitch is the rotational movement around the transversal axis. Yaw is the rotational movement around the vertical axis. So keep in mind these terms. Also, I may ask them at the exam. The translational motion along the 3 axes are heave, sway, and surge, respectively. Heave, longitudinal axis. Translation originated by the waves in this case. Along the longitudinal axis, we can call it heave. The translation around the transversal axis is sway, and surge is the translation along the vertical axis. And you see the figure here, which is it's explaining. So sway, surge, and heave. And also you have the other figure. Sorry, it's better to look at here for these terms. Okay, so let's understand, let's estimate the wave forces. The wave forces that originate by these movements. Again, waves are originated by complex and definitely nonlinear dynamics, and wave forcing on moored ships are originated by two distinguished but interacting processes. So the first process is rotational and or translational oscillation of the ship induced by an oscillating force at the frequency of waves. Oscillation may take place along and or around of the three directions of space. So the second type of wave force is called the drift force and is a net force in the direction of wave propagation. So again, there is oscillation, which is induced by waves, and its oscillation, you may have a rotational and or translational oscillation, and it may take place along or around each of the three directions of space, as I said. And then we have the drift, a net force in the direction of wave propagation. Okay, because even if waves are just a movement of energy and not a movement of mass, but anyway, they can originate a movement, a drift, a movement of the ship along the wave direction. And wave drift forces are due to absorption or reflection of waves. Again, the wave is a movement of energy, but they can be absorbed by the ship or reflected, and then this originates a drift. Okay? Indeed, waves carry momentum. We know that. When structures like ships modify the behaviors of the wavefront and its momentum, a reaction force is originated which translates into a drift force. Okay, this drift force is a steady force in regular waves and a slow varying low frequency force in irregular waves. So it's almost steady. We can assume that it's steady. Because the usual range of periods of these low frequency forces is also within the range of natural period of moored ships, the slow varying drift force may cause overstressing of mooring lines and large fender forces because there is resonance. Because the period of these drift forces is within the range of natural period of moored ships. So there might be resonance between the frequency of wave, the period of the wave, and the period, the natural period of the ship. And it is then a complex problem, and it's a complex problem, and sometimes it cannot be resolved computationally, and therefore physical modeling may be needed. And what is physical modeling? Physical modeling is experiment in lab, and this is sometimes done in Harbour engineering. So when you want to design a complex berth, a complex set of berths with interaction between waves, structures, usually a small scale model is built into the lab in order to test what are the frequencies of the forcings originated by waves over the ships and then transmitted to the moorings. Okay, so it is to better understand and to get some rules of thumb about the stresses originated by waves on moored ships, we can adopt the guidelines that you see here below. Again, the reference is Torresen. So mooring line forces are induced almost entirely by waves of period longer than 20 seconds, with major contributions occurring in the period range 40 to 100 seconds, which means that these are the waves that we have to most consider. Another rule of thumb: rolling is triggered primarily by swells with period in the 13-19 second range. Pitching is small and insensitive to the wave period, whereas heave motion tend to equal the wave height at long periods and are smaller with short period waves. So this is these three rules of thumbs are useful to identify the design wave, so the behavior of the design wave. Some relationships for computing lateral or transverse wave force in kilonewton and longitudinal wave force in kilonewton. These are relationships that can be considered empirical. The first one for lateral or transverse wave force, the second one for longitudinal wave force. Now, where are these relationships taken from? They are taken from a Spanish standard, which is a rule for Spain. It is linked. You can download the file directly from the source. Let me click on it so we may have a look. It is an interesting example. It's in English. It's titled Actions in the Design of Maritime and Harbour Works. It is very detailed. It makes use mainly of empirical relationship, and it is a useful reference. It is recognized international standard. It's also a rule in Spain, as I said. This document presents several different cases, and I just selected a very general case, which is reported here. It's also presented by Torresen, by the reference Torresen 2010, which allows us to compute in a very empirical way by neglecting most of the complexities in this process. It is neglecting resonance, and it just gives an idea of lateral and longitudinal wave force, and along the transversal direction and the longitudinal direction, depending on some basic features of the wave. The relationship has some similarity with the relationship that we saw for the wind force. This force is expressed in kilonewton. And let's have a look at these two relationships. After this description, I will stop this lecture for the theoretical part, and I will turn for the remaining time to some more exercise on R. But let's dedicate like a quarter of an hour to understand this relationship, which just gives you, by referring to a simplified case, by assuming that you identified design wave by following the guidelines that I showed above, and by assuming that you identified the design wave, are giving you, as I said, an estimate of the transversal wave force and longitudinal wave force. So let's see here what is, first of all, we look at the right hand side. Let me first of all explain what is CW. It's a coefficient which is called water plane coefficient, depends on the wavelength, which we have to have preliminarily identified at the location, and the ship drought D. And the drought is I think I have a link here. Let me see. The drought is okay. Let me find it. Ship drought, because I thought I had linked the definition, but basically it is the altitude difference, elevation difference. It's also called draft. It's the vertical distance between the waterline and the bottom of the hull or keel. So it's a difference in elevation between the lowest part of the ship underwater and the waterline, okay, with the thickness of the hull included. Okay, so CW again depends on the wavelength, ship's drought, and it is there is a figure here below which we will see that gives values. Okay, now CDW, it's called depth coefficient, depending again on the wavelength and the water depth at the location. Again, there is a figure below which gives values for this second coefficient. And here we have gamma W. Sorry, here there is a mistake. It's not specific gravity of air. Let me correct it, but it's specific gravity of water. So let me just take a note, because I need to correct this, because I made a cut and paste from the previous relationship, but it's gamma water, not air. But this is a mistake. Sorry, this is specific gravity of water is here actually, and so gamma W. Okay, here there is something that I need to correct. Definitely, it's not here. So let me check. We can check directly in the reference, which is here. Just give me 1 minute, 1 second. So Torresen is here, and okay, and here it's here are the two relationship, and gamma W, it's actually specific gravity of water. So basically what I put twice the same Yeah. Okay. So basically, this is gamma W is specific gravity of water, and here there is the mistake is that this GW is what I had to write instead of gamma W. So let me change it because I think this is something that is misleading. So I want to correct it soon. Give me 1 minute. I'm sorry for that, but because these are new lectures, as I said, in this situation, I didn't have time to revise it in detail. So I prefer, this is something misleading, so I prefer to correct it now. Give me 1 minute. Here we are. So it's not here. Here we are. Okay, so I have to get this specific gravity of water, and I need to copy it here. Good, and then this is to be eliminated. Okay, now let's save it, and I think it should be now correct. Just 1 second. Good, let me go down. Okay, now it's correct. You see gamma W specific gravity of water. Look at the values for seawater of specific gravity, and seawater here it's reported 1.034, it's tons per cubic meter, and actually this corresponds to an extreme salinity. Usually for seas, for the Mediterranean Sea, we suggest 1.024. Fresh water, you know, it's 1 ton per cubic meter. Okay, and then let's look here. We have the significant wave height, HS, which is squared. We have a coefficient D prime. Let's discuss this later. And then again, we have to multiply the wave direction. We have to take into account the wave direction, and the way we account for it is by multiply the previous product times sin square of phi. Phi has the same meaning as before. It's the angle between the wave direction and the ship center line, and here it's wave direction, not wind. And again, the sin is squared because the wave height is squared. And the wave height is squared because by squaring the wave height, we get an estimate of the wave energy. And then we have the last factor of 10, which is introduced to take into account that it's the units. Take into account the units in order to obtain kilonewton, the force in kilonewton. Now, let's discuss d prime. D prime is given by the product that you see here, where LBP is the length between perpendiculars, and the length between perpendiculars, we have a link. It's defined in this way. It's the length of a ship along the summer load line from the forward surface of the stem or main bow to the afterward surface of the stern post. You can see it here. Length between perpendiculars. So you measure along the water line the distance between the bow and the stern. So this is the way we obtain d prime. Okay, let's look at the figures. And sorry, d prime, also there is the symbol B, which indicates the beam of the ship. Let's look at the beam of the ship to define it. sorry, here there is a broken link, I need to correct it. Beam broken link, and let me now get it. Ship beam. And it's here, it's the width of the ship, the max. Okay, very good. And then let's look at this figure, which gives the values for the coefficient CW, CFW, and CDW. These figures are taken from the Spanish standard that I introduced before. And here D is the draught of the ship, H is the water depth at the location, and LW is the location depth. So I think, yeah, okay. So now, according to this relationship, as I said, we can, in a simplified way, to compute the wave force, lateral and longitudinal, which is transmitted by the ship to the berth. Here there is a final discussion on the wave loads by breaking waves against vertical walls. If your berth structure is made by vertical walls, gravity walls, then we have to consider the forces induced by breaking waves against vertical walls. And here I give just an order of magnitude. I don't discuss this forcing in detail. So far, what we did then is to consider the actions on the berth structure that are given by wind and waves. I would like next week to extend this lecture, and hopefully during the coming week I will have time to revise it before presenting. So I hope I have a reduced number of spelling errors and mistakes. I would like to discuss the action which is given by currents on the ships and then to the berths. These actions are in some locations important. Usually, as I said, the harbors are sheltered against waves and currents, but still in some locations these actions may generate important forcings. And I will discuss this next week, of course, and then I will close this topic. So what we considered, again, as I said in my premise at the beginning, is the environmental forcings generated along berths which come from the seaside. We are not considering other forcings which I will describe. I will give you a list of the other forcings that come from the land. And we are not also considering the forcing that are acting over the berths, coming from traffic load, coming from the presence of cranes that allow us to upload and to load ships and unload ships. And I'm not discussing these type of forcings, as they are more related to civil engineering design rather than harbor and coastal engineering. And also you learned in other courses how to estimate this forcing from traffic load and also soil pressure, etc. So it's my treatment doesn't go into the fine details. This is just an introduction. I want that you have clear what are all the forcings, and as I said, I will provide you an extended list in the next lectures, and I wanted to give you an idea on how estimation of environmental forcing coming from sea can be approached. This is the level of detail that I am inspecting. Okay, I would like to give you 1 minute for any question, and then I'll take some time to again pass to R and moving forward with our introduction to RStudio. Just let me know now if you have any question. And I apologize if this last part was not was affected by some imprecision. While you are asking questions, or while are you taking your time, I'll make a change here of the last two imprecisions. So I have to change here wind with wave and the broken link. You see that the final part of the lecture is not yet published. Okay. So let me see. I don't understand why it didn't work the link. I'll have a look now. Okay, now it works perfect. And this is wave direction. Okay. Okay, good. Okay, so if you agree, I think we can start RStudio. I just would like to know if there are any problem. I remember that last time there was a problem with RStudio. I think it was one of you. I may make confusion with the other students. So just let me know. You can see my window with the RStudio open. Just let me know if you can't get to this. Yeah, okay, you solved it. Thank you, Camilla. Perfect. Now, I just would like to make a first example. Okay, you downloaded the wrong program. Okay, I'm happy that you solved it. I just would like to make now a step forward. I am not sure. Let me just 1 second. I want to see the history of our previous exercise because I want. Okay, I think I want to give you an example before we move to the solution of a practical exercise. I want to give you another example of how functions can be used in R and how then we can use R for programming. And so far we mainly dealt with the console. So let me first of all remove this. I want to get a clean, I want to remove this data set, global environment. So I am quite sure that there must be, there are other, okay, so let me see list, okay, good. I just wanted to, there must be an easy way to remove all the variables from the global environment, because here I have previous variables that I want to remove. Just give me 1 second, because I know the usual way of removing that, but I just would like packages. Okay. I just would like, let me see. Let me see if I select all of them. And okay, good. Now I think it must be if you find a way to, if you find your way to remove all of them, I just want to clean. Otherwise, I do it with the console, but I am trying to, let me see. Not this. I am sure there is the way to, so this is saving. Okay, import. Okay, here it is. Sorry. Yes, I didn't see I mean, I was looking for the trash bin. Instead, it was very simple. Okay, now let me, environment is empty. I just wanted to get an empty environment. Now, as I said, when we turn to programming in R, it's better to open a script. And in order to open a script file, we have to click on File, New File, R Script. Oops, sorry. File, New File, R Script. Here it is. So we have this script file. It would be better to give it a name. So let's call it my script.r. And this was, in order to give the name, I just click on Saved. I just clicked on Save. And let's create now a function to draw polynomial function, a polynomial line. And this is a nice example in order to understand what functions may allow us to do into R. In order to create a function, let's call it my function equal to, this is the definition, the way we define a function, and to define a function we use the function. It's a function of R, and you see that when I started writing it, you see that the menu gives to me a list of choices. If I click on function here, then I get already the completion of the instruction and the 2 parentheses. As you may remember, functions in R have arguments, and this is precisely what I have to place between the round parentheses. I need to put arguments here, and let's put 3 arguments, A, B, C. I will explain you later what they are. Okay, no defaults. If I put something like A equal 1, this is a default value. Okay, let's put a default value for A, no defaults for B and C. Okay, good. Now I can go to a new line, and let's put curly brackets, because a function is indeed a program. A program is a sequence of instructions, and this sequence of instructions needs to be placed between curly brackets. So let me put there a pair, 1 instead of A. No, I wouldn't say this. If you put just 1, you are not assigning the value to a variable. The purpose of defining the arguments is that you define variables inside the function. So in this case, by writing a equal 1, I mean to say that I'm defining a variable inside the function with a default value of 1. If you just put 1, when you call the function, you can put 1 in the first place, but for the function call, let's wait. And in this case, you are defining the function. You are not calling it. You are creating a script that tells her what is your function about, tells her the definition of your function, and therefore you have also to define the variables that you use into the function, those that you want to use arguments, but you will see later, I think you will better understand. So curly brackets, again, I press at the same time Alt, GR, and 7. And these are my two curly brackets, and then I placed a new line between them. So you already identified the start and the end of your function. Very good. Now, I said that I want to draw a polynomial function, so let me define it. Y is equal to A plus B times x to the power of c. This is my polynomial function. Okay, A is in coefficient, let's say an intersection coefficient, which is the value that y takes for x equal to 0. And then x is my independent variable, which is multiplied by b and raised to the power of c. Okay, now I need to define the independent variable. The independent variable, let's put it here. I need to define it before it is used. So let's create a sequence between minus 100 to 100 with a step of 0.1. This function sec defines a sequence between a lower boundary, minus 100, upper boundary, 100, with a step of 0.1. So it's the length of the range is 200. With a step of 0.1, I get 2000 values for x. Now y is computed. And now let me plot it. Plot x, y. And let's use a line as plot type. And then that's it. This is my function. Now I have to upload it in R. In order to upload it, let's select it and press on source. And you see that in the console, it appeared source myscript.r. Very good. Now let's try to run the function. My function, I can do it in the console. My function of 1, 1, 1. What are you expecting from here? Or let's say 0. In this case, you see, Camilla, that I am not writing A equal to 0. I can do that. I can write A equal to 0, B equal to 1, C equal to 1. But for simplicity, which would be faster, I can just write 1, 1, 1, 0, 1, 1. The important thing is to remember the order of the arguments. If you just give 3 numbers, then it assigns 0 to the first, 1 to the second, 1 to the third. If you don't remember the order, it's better to say something like C equal 1, B equal 1, A equal to 0. You see that I didn't respect the order in this case. The order, the argument are defined in the function. I didn't respect this order. But if I name the variables by name, I can also give a different order. Now, what I am expecting from here, I'm expecting to get the plot of a straight line passing by the origin, which is indeed what I am getting here. Very good. So you see how it works. We define the function. Let's make another attempt. I got a sorry, I don't understand why, so write again something more if you have some other questions. So my function of, let's make another experiment. Let's make an exponential function. So we may find 1. Okay, yes. Let me just run the function a second time. And B is, we can use 1 and then 2. You see that this is an exponential function, which is fine. You may say the plot is not really nice, but let's postpone this. So your question is, how do I copy to source? So, as I said, you first of all have to source the function into R, and in order to do that, in RStudio, you can do this. You select the function and you click on source. I'm sorry you don't see the mouse, but you see that there is displayed the black box which indicates that my mouse is there. And this is the command which appeared in the console. Look, you can also work in the console directly. If you call back, give me 1 second, I have a call and as usual I need to reply, just 1 second. No, sto facendo lezione, ma non preoccuparti. Sì. Allora, io so che ho 2 docenti di chimica, di ingegneria chimica che stanno facendo delle prove in laboratorio su questo da stamattina. Ho fatto aprire il plesso apposta, quindi secondo me stanno lavorando proprio. Può essere, però in ogni caso bisogna che ti reindirizzi a loro, quindi praticamente se... non ce li hanno. Perché aspetta che ci penso, e dunque loro hanno a che fare con la BOI e con Paglianti, quindi hanno quindi già a che fare con chimica industriale, perché Paglianti è a cavallo, la BOI secondo me, aspetta che ci penso, no, io direi che... però la BOI appunto secondo me sa, se ci fossero altri colleghi che hanno a disposizione quello strumento, lei lo saprebbe. Sì, perché comunque allora mi ridescrivi che poi magari faccio una veloce ispezione, mi dici ancora che... flussi d'aria fino a 30 litri al minuto, quindi l'hanno già chiesto a voi. Va bene, dai, adesso se dovessi avere delle news ti faccio sapere. Perfetto, grazie, ciao ciao. Here I am, sorry. So, as I said, you can source your function also working on the console. If you clean the console, Control L, and you call back the previous command, you can also run it from the console. Okay, so as I said, now let's embellish a little bit this plot because it's not nice in this way. And so I work on the script. So the instruction is plot xy. Just 1 second, I want to connect the phone because I can't see. Okay, now I see my screen also in the phone. I find it very useful if I also connect the phone because I see over the phone what you see in the screen, and with the delay that I hope it's the same your delay, so I can realize what you see and what you don't see. Okay, good. As I said, let's embellish this plot. First of all, I suggest that we make the line in red, and I suggest that we make a line width equal to 3 increased. So we can select and source, and then I may redraw the plot. I'm now working in the console. Now you see that there is a red line that appeared. Let me go back again to the script and put a grid here. It's grid, just grid. And then I can source it and redraw it. Now you have a grid. And another thing that we can do is to put label in the axis, but I would say that it's really not needed. We have already X and Y. And what is interesting is to look in the plot window for export, and we can save it as image or PDF. And if we save as image, then we have a window that opens with the image format. PNG is fine to me, and width and height are as given here. I would like to let's increase it a little bit, 600, and update preview. I don't see anything more. Okay, and let's put in view plot after saving. File name, let's put my first plot. Good, and then we can make save. Okay, here it is, and it's opened, and you see that it's indeed nice, and it is squared because I gave the same width and the same height, and I got it. I could also get it in PDF, which is anyway fine. If you want to embed the graph in a Word file, it's better to use a graphical format, a graphics format like PNG or JPG. If you want to produce a printout, the PDF may be better. And then you can close this window, and then we are back here. So this is an example of a function, of a script, and I think that at this stage we are ready to write a program that applies to one of our cases. And so far in our lectures we didn't get any particularly complex problem to solve. So I would like to refer to an exercise which applies a concept, or better, a model that we studied last semester. During my 3 lectures that I gave in October and November, I talked about beach morphology, and I introduced a model to study the dynamics of beach morphology. And this is precisely the model that I would like to apply by elaborating a high-level R exercise. So if you don't mind, I would like to go back to that lecture and get the exercise from there. So let me go back to it. Let me just check if I put also the exercise here in the tutorial of Harbour Engineering. I'm just no, it's not here. So I'll put it in this our page of Harbour Engineering. For now, there is again the estimation of extreme wave height. I think this is the exercise that we developed together during the last semester. But now I would like, as I said, to get something more complicated, something more interesting. So let me go to a web page where this can be found. Here. And here is application of the CELC formula. And can you please tell me if can you please confirm to me, I am sure that I did it, but can you please confirm to me that you all attended my lecture on the CELC formula, which is this one? Just 1 second. Here it is. This is the lecture that I used. Okay, Camilla, yes. Is there somebody that didn't attend my lecture on that? I think we are 4 students now, so I would appreciate if you could tell me. And it is here. So I assume that everybody attended it. I just want to remind you what is this formula. This formula, it's let me see, I attended last semester. Okay, very good. So this formula allows you, I just remind you, to estimate a long-shore sediment transport. It's just a long-shore sediment transport. And it assumes that a long-shore sediment transport, it's proportional to wave energy. So it's based on the computation of wave energy, and in particular computation of the wave energy at the breaker line. And then the sediment transport is assumed to be proportional to wave energy. And then again, this is a long-shore sediment transport. I introduced briefly a model that allows it's called the one-line model, allows you to compute the evolution of the beach profile after they computed a long-shore sediment transport. And what we do basically with this model is to assume that the beach profile is unchanged. It just moves seawards by keeping parallel to itself when we have a net increase, net deposition of sediments, and it moves backwards when you have a net erosion by remaining parallel to itself. I just want to draw on this image what happens. So let me draw it. So this is the image. So what you see here, it's a piece of coastline. It's a delta y. Y, it's the abscissa measured along the coastline. So again, it's a piece of coastline. And then you can compute from each piece of coastline the sediment transport along shore, which for instance here it's assumed has Q in. So it's sediment transport entering. It may be positive or negative. If it is positive, it means that there are solids entering the piece of coastline. If it is negative, it means that there is erosion. Okay? And then you make the same computation for the next piece of coastline. When the difference between the two sediment transport is positive, meaning that you have deposition in the first piece and reduced sediment transport downstream, so you have a higher sediment transport upstream in the first piece and a reduced sediment transport downstream, it means that there is a positive difference between sediment transport, there is deposition and accretion of the beach. If the difference is negative, you have erosion because you have a higher sediment transport downstream than upstream, and therefore higher sediment transport means that there is erosion. So basing on the difference between sediment transport in two adjacent pieces of coastline, you can assess whether the beach in that piece of coastline is accreting, expanding, or eroding. And this difference in sediment transport is the yellow volume that you see on this figure. This yellow volume here. Okay? The question is whether this yellow volume translates in a movement seaward or landward, whether it is accretion or deposition. And we estimate this by analyzing the difference in sediment transport between two adjacent pieces of coastline. And if we assume that the beach profile, which is this one, moves parallel to itself in the new position, these two segments are parallel, which means that these other two segments in blue have equal length, 1 and 2. If we also estimate that the beach profile in the vertical direction, this one in blue, moves parallel to itself, which means that these two segments, let me indicate them in light blue, have equal length, then we can easily estimate this quantity here. Just 1 second, I need to highlight it. Delta epsilon, you see this delta epsilon here we can easily estimate it because we know the geometry of this volume, of the yellow volume. We know everything because it is surveyed at the beginning. So let me go back. These parts are surveyed. This is surveyed. It's original shape of the coastline. And it's simply moved forward here. So the geometry of this volume is perfectly known, but delta epsilon, which we can easily estimate because we know actually the yellow volume. The only unknown is delta epsilon, and we can estimate it. We can estimate it by knowing the volume. And what is the value of the yellow volume? It's the difference between a longshore sediment transport in two adjacent pieces of coastline. So if we have a given coastline with a given wave forcing, because remember, to estimate a longshore sediment transport, you need to know wave forcing. And in particular, we need to know wave direction and wave height at the breaker line. If we know the wave forcing, if we know the original shape of the coastline, the original geometry, then we can easily estimate a longshore sediment transport, which is the yellow volume. It's the difference between a longshore sediment transport in adjacent pieces of coastline. We can estimate the yellow volume, and we can then estimate the delta epsilon. The delta epsilon may be negative or positive depending on the considered piece of coastline. And as a result, it will happen that the shape of the coastline in each individual piece is unchanged, the profile is unchanged, but delta epsilon will be different from one piece to another, and therefore the overall shape of the coastline will become different. The model in principle is simple to apply. We just have to decide the delta y here, which is the discretization step for the abscissa along the coastline. And then we need, for each delta y, we need to estimate the angle between the between the waves, the design wave, and the coastline itself. This angle may change because the shape of the coastline evolves in time, and then the angle may change. We have to estimate this angle. In this way, we estimate the longshore sediment transport, and then we can get an estimate as time passes of the evolution of the beach morphology. But this is, this looks a bit complicated, so we need definitely a computer program to do this. And this is a nice example of a problem for which we don't have a commercial program at hand available. Actually, there are commercial programs for solving this problem. And also these commercial programs allow us to remove some of the assumptions that we introduced. This model has a very important underlying assumption, which is the steady behavior of the beach profile. It's not steady. It is the beach profile changes, the beach slope changes after accretion erosion. So there is this important assumption underlying our computation. As I said, we may have commercial program, but let's pretend that we don't have them, also because they are costly. So the question now is, can we write a program by ourselves that allows us to solve this exercise? Now, let's have a look at the text of the exercise. I think I introduced the concept. I reminded you the concept. And for sure, this is an exercise that is more complicated with respect to the one that we did before. Let's see whether we can, let's see the text of the exercise, as I said. So the text is here. I will put this link directly into the page of Harbour Engineering soon. As soon as I close this lecture, I will go there. For now, if you want to make the download now, I don't think we really need it, because I think you can download it later. And as I said, as soon as I finish the lecture, I will make this change. Now, let's look at the exercise. And if you click on exercise application of the CERC formula, now you are not able to click on it, but you will be able later. This is the exercise. Sorry. Let me just reduce this. Okay. So it's application of the CERC formula to study the evolution of the coastline. The geometry of a coastline is described by the coordinates along the x-axis given in the first column of the file, which is given here. And actually, it's better if I update here the... Okay, but you can use this link, no problem. And the second column reports the limiting geometry of the shoreline, which would be attained if a significant erosion occurred. So there is also a limiting geometry. A limiting geometry may be dictated by seawalls or by the presence of structures, other structures, etc. And the coordinates are equally spaced with a step of 150 meters. So our delta y, let me go back here, delta y is 150. And the time step to be adopted is the one given here. It's expressed in days, so the number is quite small. So the beach is subjected to have a wave forcing that is described in this other file. Again, this is an old link, but it's still working, so you can use it. The first 3 rows of the file report the spatial step along the y-axis, the time step, and the length of the simulation in terms of time steps. We will have a look, let's have a look at this file. I am just copying it. Actually, I need to put it here, so this, okay, and it's size, oops, sorry. This, I am not sure whether, sorry, size. When you will download it later, I'll put the updated link. I think it's better. So it's size default files Didactica, and it's called coastal and wave forcing.txt. Let me see if I can open it. Yes, here it is. So this is the file, the data file. And if you look back to the description in the PDF, the first 3 rows of the file report the spatial step along the y-axis, 150, the time step, and the length of the simulation in terms of time steps. So let's go back here. It's 150, This is the time step in seconds. It was expressed in days in the PDF, and it's now given in seconds here, 120. And the length of the simulation is 1000 time steps, which means 2000 minutes. And then you have these columns. And these columns, let's see what they mean. The first, the following 5 columns report: 1. The position of the wave breaker line. It's the coordinate, the x coordinate of the position of the wave breaker line, not required for performing the simulation. Okay. And then the wave height at the breaker line, the wavelength at the breaker line, the sea bottom depth at the breaker line, and the wave angle alpha with respect to the y-axis. It's important that you read here. The wave angle is equal to 180 degrees when waves are directed along the y-axis and oriented towards increasing y's. Alpha 2 is the angle between wave and coastline. Okay. And then, so we have here, again, let's forget about the first column, which is not used, position of wave breaker line. So we have wave height, wavelength, 103. If I look at the first one, is wave height, wavelength is 11 meters. And then we have here, if I will remember, sea depth, let me see, sea depth, and the angle here, okay? Now, I think we can stop here and we will move forward next week. Please, in next week I will explain you with a drawing something more about this wave angle. And meanwhile, please have a look at this text, have a look at the data files, and it would be interesting, I'm not sure, it's not very easy, if you were able to upload this data in R. In any case, we will do it together, but if you have some time during the week, I would appreciate if you could make an attempt. So now, as soon as I close the lecture, I will make this link available. I also will correct the file so that you get the updated link, and that's it. And then next week we will start by talking about current forcing, and then I'll dedicate, I would say, a couple of hours to this exercise. Any question? Okay, thanks, Camilla. Okay, very good. If you have any question, you can write on the chat as usual, and once in a while I check. And also I'll put in the chat some links to keep your interest high during the week. Okay, thank you very much, and let's meet again next Tuesday, same time. Thanks a lot. Goodbye.